Last lesson ended at a wall. The inverse transform needs F inverse, and the normal distribution does not have one. Its CDF is an integral with no closed form at all. So inversion is simply unavailable. But look at what we can still do. We can evaluate the density itself at any point we like, cheaply. That turns out to be enough, provided you stop trying to invert anything and start throwing darts. Pick a proposal density G that you already know how to sample from. Thanks to last lesson, that list is long. Then find a constant m large enough that m times g of x sits above f of x everywhere. That product is your envelope. Now the algorithm. Draw a candidate x from G. Draw a uniform U. Accept the candidate if U is at most f of x over m times g of x. Otherwise, throw it away and start again. Every accepted x is a draw from F. Here is a concrete pair. Target, the standard normal, the very distribution that defeated us last lesson. Proposal, the Laplace distribution, which the inverse transform samples in one line. The smallest valid m is 1.32, and the envelope touches the target at plus and minus 1, exactly where the ratio is worst. Why does it work? The two random numbers together place a dart uniformly in the region under the envelope. The x picks a column with probability proportional to g, and the u picks a height uniformly within that column. The accept test keeps a dart only if it landed below F, so the darts that survive are spread uniformly over the region under F and nowhere else. Everything in the gap between the two curves is discarded. Now read off their x-coordinates. The chance that a surviving dart sits in a thin slice at x is the area of that slice under F, which is f of x times dx. That is exactly what it means to have density F. The accepted samples are exact draws, not approximations. Nothing is free, and here the price is the rejected darts. The region under F has area 1, because F is a density. The region under the envelope has area m. So the fraction of darts you keep is exactly 1 over m. That makes m the entire story. Our normal from Laplace pair has m equal to 1.32, so about 76% of candidates survive. Cheap. An envelope with m of 20 would throw away 19 darts out of every 20. And this is where the method breaks. In high dimensions, any envelope you can actually construct tends to overshoot the target by a factor that grows exponentially with the number of dimensions. M explodes, the acceptance rate collapses, and rejection sampling becomes useless. Rejection sampling. Envelope the target with m times g, throw darts uniformly underneath the envelope, and keep the ones that land below F. The survivors are exact draws from F, and you never had to invert anything. The cost is 1 over m. The tighter the envelope, the less you waste. And a loose envelope, or too many dimensions, kills it outright. You can now generate samples from essentially anything. Next, what they are actually for. Averaging a function over your samples estimates an integral you could never do by hand. Monte Carlo integration.